Good morning to all of those people who have joined. Thank you for joining us on a Saturday. And we just have the numbers increasing as and when people join. I'm just going to give you guys like an intro to CTO Talk. For those of you who are new, CTO Talk was founded as the first go-to tech content platform for CTOs and by CTOs and aspiring CTOs. And we're all here to learn and network and take this community initiative forward. So we're here to discuss topics around tech, software, engineering, and these are talks given by CTOs towards the community. So it's like a page forward initiative which we're doing. And so until now, CTO Talk has grown up to 2 seasons of deep dive talks about for 14 episodes, and we have a community of about 5,000 plus tech professionals today, and we're very happy to onboard all of you new people today as well. So this is how it used to look, as we call it, the pre-COVID era. We used to meet up. We have a wonderful grass court here. And this is how meetups used to happen. It used to be ultimate fun, and the interactions used to go an hour and a half after the presentations. But now it's all virtual, and nothing could stop us. So we've been continuing with the virtual editions of CTO Talk, and here we are today as well. So this is the 3rd episode in season 2, and so what we're planning for is what you're attending right now is the deep dive, and we have a bunch of new content ideas coming your way. So what you can look forward to is CTO Talk 9 Yards, CTO Talk Boardrooms, and a CTO Talk annual edition as well. So we'll be mailing you soon, and so watch out for our mails from our ID, and we hope to involve all of you and the whole community and all of these coming the new content ideas. So if you want to keep in touch with us and know what's happening in the community, please follow us on LinkedIn at CTO Talk, or you can write to us if you want to volunteer with us and help us grow, or even if you have any suggestions, write to us at contact@ctotalk.in. So Kissflow is our main title sponsor, and we're ever grateful for them for all the support from Suresh and Kissflow, and our community partners, Startup Grind, NASSCOM, and TIE. On to today's session, we have Niraj Rajmohan from Ultraviolette Automotive. He's the CTO, and over to Dinesh, who's the VP of Product Management from Kissflow, to give like a kick-ass introduction to Niraj. Over to you, Dinesh.
Thanks, Vita. Good morning, everyone. We all know the future is electric. The electric mobility is literally transforming what we are driving even today, correct? So it's always very exciting to listen to the pioneers who are forging the path for electrical mobility in India. So it's with special excitement that I'm pleased to welcome Niraj, the founder and CTO at Ultraviolette Automotive. Before going into the typical welcome note, I want to just share a slide so that you guys are really interested in what he's going to share. Right. So this is what he's going to talk about. If you look at it, this is a fine combination of hardware, IoT, electronics, and software, along with beautiful design, right? And that's what Niraj believes in as well. And Niraj is going to enthrall us with the presentation for the next 1 hour. I'm extremely excited to listen to what he's going to talk about in Ultraviolet, and hope you are excited as well. I welcome Niraj to take the stage and enthrall us with what he's doing, what he and his team is doing at Ultraviolet. Welcome, Niraj.
Thank you, Dinesh. Thank you, Shweta. I'm quite excited to be here. Haven't done such a sort of presentation to a large crowd online so far, but this is an exciting opportunity. I think what has been happening over the last 5 years since Ultraviolet started is that we've been building a lot of stuff internally, and as most of you may be aware, building hardware is difficult, right? It's time consuming, it's difficult, and the things that we have learned over the years, we'd like to share it so that there are more companies, more ideas, more startups that evolve in the space, and also that people sort of build the skills that it takes to be part of this hardware revolution as well, right? And let me share my screen. So how I've structured the talk today is basically around, a little bit of my background about the things I've done in the past, which is sort of relevant to what we're doing today, because I actually started my career in the software industry, right? So I studied information science, computer science, had a job in, what is typically a software company in the internet space, right? And it's a drastic deviation that my career has taken from where I started to what I'm doing today. But if you look at it from the point of, okay, these are the few factors or these are the career options that are available. But at the same time, if you go back and see what I've been working on, it's very much in line with what we are working on here today, right? So I'll just go a little bit into my background and then start talking about ultraviolet. And the way that I've structured the talk here as well is so that everyone sort of here gets an idea about what it takes to build hardware, right? Typically, in India, at least, software companies are quite widespread. From embedded system software development to all the way to system software, application software, web-based applications. So all of these are quite prevalent in India. But when you see how sort of hardware is built, I think that gives a different perspective, and that's what I focused my talk here today. So let me just share my screen and we can get started. And yeah, I think we can get started from here, right? So a little bit about ultraviolet before I sort of jump into more details. At a very high level, what is this company? I'm not sure if all of you are completely aware what the company does. Our product will be launched towards the end of this year in the market, but we have been working on it for over almost 5 years now. And the first product that we are going to be launching is the Ultraviolet F77, right? This is a fully electric motorcycle. It is comparable to a 300 to 500 cc internal combustion powered vehicle, and it is meant to outcompete all petrol powered motorcycles in that same segment. When I say outcompete, I mean in terms of 0 to 60, 0 to 100 acceleration, top speed. What you see the numbers on the left there is actually what we have achieved with our vehicles, our various pre-production vehicles, right? And so this is a very particular segment, a specific segment that we are targeting with the first product. And so far, the response has been overwhelming in the sense that it's not just in India, it's globally. So we've received interest for these vehicles from over 180 countries, right? And that's a pretty crazy number out there, right? And it's going to be a while before we can start deliveries in all of these countries, but we're looking at first starting out in India towards the latter half of this year, right? Now, this was sort of to give you an idea about what is the end outcome going to be in terms of the first product as such, right? Now, to go into some more detail about where I'm coming from and how this company started, let me give you a sense of, so I'm one of the founders. I'm the guy on the right that you see there. I'm Niraj. I finished formally my education has been in information science, and I also have an MBA degree. I've previously worked at companies like Yahoo and NetApp. I've previously had 2 other attempts at startups as well. And what I want to do here today is sort of give a sense of how that journey has evolved to come to where we are now, right? And before I go any further, so my co-founder Narayan, who you see on your screen, comes from mechanical engineering and automotive design background. He's previously worked at companies like Volkswagen in Germany, Toyota Daihatsu in Japan, before coming back to India and starting Ultraviolet. So both of us had been contemplating various ideas. I have known Narayan since school, and both of us go back a long way. So I'll now get into a little bit about my background and how I have come into this field that we're talking about today, right? So I've tried to create what is sort of a personal timeline, right? In terms of how my career has changed over time and how it has come into this particular area. And at the outset, if you zoom out, it looks like this. It looks, for me, I don't consider sort of my technical career to have started at the point where I graduated from college and took up the first, job. For me, it actually starts way before that. It started at the point where I started programming in C, right? And believe it or not, it was when I was about age 10. And it was a few years after I had my first computer. But the idea that I could build something and or sort of get a machine to behave in a way that I wanted it to behave was where the whole process of creation started for me, right? And that's where I consider as a starting point, and that actually happened a really long time ago. Now, if you look at it in terms of career choices or academics, you'll see that there are a few things. Like, I graduated from engineering, I took up a job at Yahoo, I had one startup, then I decided to do an MBA, worked as a product manager with another large company, another attempt at a startup, and this is the third company that I sort of attempted to start. And so this is a very sort of high level overview. But if I dig back a little bit, I think the actual sort of real content is in actually the phases or the time between all of these lines, right? It is not about particularly joining a company, it's about what you're doing at that company. And for me, all of this history about what we're building hardware today actually goes back a long way into what I was doing earlier as well, right? Just to give you sort of an early timeline. So while I started programming in C, I was building, command line applications. I was interested in, I had access to the internet at a very early age. Even before the internet, there were, these bulletin board services, BBSs as they were called. And that was my first exposure to networking, to TCP networks, file systems, Unix, Linux. And there's a sort of recurring thing that I've seen over the last 20 years, which is that I have frequently encountered problems 6 or 8 or 10 years before I sort of had the solution in a structured way to those problems, right? So when I was talking about programming in C, I was talking about, I was studying from books like C for Dummies and things like that. They're terrible books. Some of the other books are clearly better. But when I started programming, I would encounter all of these problems like time complexity, space complexity. And it was almost, I think, 8 or 10 years later in engineering that I actually found structured solutions to these problems, right? So it's, for me, that recurring theme is that you're trying to solve a problem with insufficient information, and it takes a few years to even have the ability to know what you're looking for and to have a conversation with a professional in that space and to sort of find a structured solution to what you're trying to do, right? So that's where it all started, from programming computers, from networks, trying to find ways to exploit networks. So this was happening at a very early age. My first hardware upgrade was, actually from going from a 486 to a Pentium processor, going from a 14.4 kilobit per second modem to a 56 kilobit modem, right? And this is where it all started. And along the way, by the time, I had reached a pre-university grade, I had already built certain comfort in terms of programming in C, C++, a bunch of languages. And I decided to take up electronics as a pre-university course for 2 years, right? And again, this was the time where I was first introduced to transistors, a lot of prototyping on analog electronics. And frankly, to tell you the truth, even though I scored, in the high 90s and things like that, the real application of all of that is actually happening as we speak in the last couple of years. And it was just setting the foundation for the things that would later happen in my life. So this was, early 2002, 2004. And then things really started to pick up. So I joined an engineering college in Bangalore, BMS, College of Engineering. And this is where, I had taken up computer science, information science. And beyond the regular coursework, that's also when I also had Narayan in the same university. He had taken up mechanical engineering, and we started working together on various projects. Actually, there's another participant here today as in the audience who is also part of that picture, Vijay Rai. So that's Narayan, that's me, that's Vijay. So we go back a long way, and this was one of the projects that we started working on. It was we started building different kinds of boats, cars, planes, and these were meant to solve different problems at different engineering competitions. These were creative engineering competitions, or things like IIT Shastra or Tech Fest. And what happened is that over a period of about 4 years during engineering, we ended up winning about 35 to 40 competitions. And all of this that I'm talking about is before, like, I've taken up my first job, right? And this is the kind of exposure that we had back then to hardware. That's where the first time we were exposed to lithium-ion batteries. That was the first time we were building, very robust electronics, even though it was for a single device. But imagine being able to withstand different kinds of terrain, different kinds of water, different kinds of, immersion, and you still have electronics which is required to work. And so the solutions that we would use then obviously don't scale to what we're talking about today. But the point was that we were dealing with very fundamental problems even back then. And so this is what was happening at the time till sort of we completed our engineering in 2008. But the point was that we had experience working with cross-functional teams, from mechanical engineering to electronics to computer science, and all of this was coming together and being integrated in various forms. So, and we had several failures along the way. It was not that everything was hunky-dory and we would always win these competitions. It was usually a few months of effort, and in certain instances, on the final day, the car that you see on the left there was a 3cc engine-powered car, right? And it blew up in our faces at IIT Bombay, if I remember correctly, in one instance, right? And so there was no way to recover from hardware failures usually in a short period of time. And that's where it all started for us, right? Now, the reason I'm bringing up all of this is because, like I mentioned earlier, there's a recurring theme that I've noticed, which is that you start trying to work on a problem, and it's several years later that you actually realize the value of the problem that you're working on and the solutions to that particular problem, right? Now, the next phase that I went through personally was working with some large companies. So I started my career, I had a campus placement opportunity with Yahoo in India, worked with what is called their media team, typically news, sports, lifestyles. All of these properties, again, this is going away from hardware. This is completely into software, web scale architectures, thousands of systems, tens of thousands of systems, hundreds of requests per second, different types of database technologies, different kinds of constraints in terms of requirements, where even a minute of downtime meant that the company would lose thousands or tens of thousands or hundreds of thousands of dollars. So my job there was, as a systems engineer, to make sure that all these systems are operating at an optimal level. So the developers would work on a single module which is there on the website, or a particular technology, but when it all came together and it had to scale to millions of people who are either watching, looking at the stock market for quotes or looking at live scores for sports, all of that was being implemented by the systems and the operations team, and that was where I was coming in, right? So it would be frequently at 3 a.m. I would be awake because there's a particular basketball match going on in the US, and hundreds of thousands of people or millions of people are trying to track the score. And even if there's a second's delay, then that's a problem, right? People are not getting live scores. So my problems, actually being able to solve problems at a very large scale, started there. And that was a very interesting experience for me because I frankly hadn't dealt with that, right? Now, looking at what I was doing back then, a lot of the architectural decisions around how do you build, a cloud application, all go back to the time that I spent at Yahoo in terms of, how databases are designed, what kinds of databases. Started going back to, working on some kinds of different basic hardware. So one of the things that I wanted to work on, and this, I was talking to Narayan back then as well. Oh, one of the things that I mentioned, I think I forgot to mention, is that the timeline that you see on the screen, I have known Narayan the entire time from 1996, where we were in school together, all the way up till now, right? So there's a shared history with Narayan since then. And so even the projects that I was working on, Narayan was involved there as well. So when I started working on trying to build something very ambitious, this was trying to build, autonomous drones, completely autonomous drones, which was intended for, terrain mapping. This was the days before Google Maps, was, highly accurate in India. You had very pixelated roads, things like that. And this was a time where, and I think this problem still exists with drones today, which is that you have limited flight times, all the way from 20 minutes to 40 minutes. You don't have drones which can typically fly more than that, right? And the problem that I was trying to solve back then was, why can't we have drones that fly longer, right? Is there a possibility of having like minimal downtime, which means that the drones can either charge themselves on the fly, which means from power lines, or have modular batteries which can be replaced very quickly. Now, this was a very, very ambitious project, and after working on it for about a year while still at Yahoo, on weekends I would be tinkering with hardware, trying to reverse engineer existing hardware, trying to build my own electronics, PCBs, and frankly, I did not have the skills required to do all of that, right? And that was the first set of failures that I encountered, that even if I had to build something like this, it would be a much larger scale. It would require a larger organization. It would need a team of experts, and all of which I did not have access to. But at that point, I did not know all of this. I quit my job at Yahoo to pursue this full time. And while we built prototypes and all of that, it really didn't take off in the sense that I expected, because frankly, there was a lot of work to do, right? It still is an ambitious project, even if you talk about it today. I think there are a few drone companies, but no one's doing the kinds of things that I was hoping to accomplish more than 10 years ago, right? So and I sort of started to see the limitations of what I was doing back then itself. One of the things had to do with actually, how do you build a company? How do you scale it? How do you, all of the money that I had saved up from my salary at Yahoo sort of got spent into this project. But at the same time, I wanted to sort of scale this to something larger, but I did not have an understanding of what it would take. So even though I am the last person, I was still at that point considered to be a sort of technical person. I decided to do an MBA just out of curiosity, to see what sort of, to understand finance, economics, product management, these topics, so that I could apply them to my work and sort of start things from scratch again if I wanted to in a better way. So that's when I decided to do an MBA. This is from the Asian Institute of Management in Manila. Then I came back to India, and along the way, again, there are numerous other projects that I worked on. In 2012, there was a hackathon organized by Yahoo. At this point, I had left Yahoo, but there was an all India hackathon being organized where about 800 participants were there, about 170 teams were there. And frankly, when I went to that place, I did not know what I would be working on, right? It was a 24-hour hackathon. And one of the problems that I chose to solve was something that was bothering me for a long time, which is that while reading documents on the move, on an iPad or any tablet, you're trying to read a PDF file. If you're in a car or a bus or a train, you sort of end up getting nausea or fatigue because of the eye strain, because of the vibration, when you're trying to read some small text, right? So I tried to solve that problem in a period of 24 hours. So this is just to give you an instance of how I was trying to solve the problem. So I used accelerometer data on an iPad, try to identify low frequency vibrations from the engine or the train, and used that information to compensate and move the image in 3 dimensions on an iPad, just to reduce eye strain. So I also had another objective, which was to use the webcam to see how the person is also moving, and sort of use that information to stabilize the image. But I couldn't get to that, right? That was the larger goal that I wanted to achieve. But the first part of it, I did manage to solve. And that's why I won. I was one of the main winners for the competition. It was a pretty big deal because I managed to accomplish this in less than 24 hours, right? So these are the kinds of problems that I had been tackling. And this was something that I did during my MBA. So I'd come down to Bangalore. I wasn't very keen on doing any internship with a business sort of entity. And this is what I was doing in the meantime, right? After that, I went on to work at a company called NetApp. This is again a Valley-based company. I was a product manager with what was called their, advanced technology group, or the office of the CTO. And my job there was to work on future products. It was to work with a research team of about 30, 40 PhDs, postdoctoral researchers, and to sort of commercialize their research, or drive research objectives through understanding market requirements. And this involved things like taking IoT devices. If there are millions of smart meters, how do you analyze that data in real time? How do you detect anomalies? How do you operationally use this information? How do you take all the streaming data and make, you know, viable architectures out of it? So those were the kinds of problems that I encountered. I also had another company along the way called Now Technologies. This was for a brief period of time before Ultraviolet, but sort of this is how many attempts it took for me to find something that, you know, sort of became what Ultraviolet is all about today, right? So that was sort of, I spent more time than I would have wanted to on my background. But now what I'm going to be talking about is Ultraviolet, which we started in 2016. And like I mentioned, Narayan and I go back a long way. And one of the common themes that we had been working on is that we knew we would end up doing something that involved, you know, cutting edge technology and at the same time mobility. So these were two themes that we frequently came across in our past. And that's when it all started to come together at Ultraviolet. Now, before I sort of jump into specific areas about Ultraviolet, let me just give you a sort of brief idea about the inception of the company, right? In the meanwhile, if there are any questions, I'd be happy to take them. Please feel free to, I'm just checking the tabs. So far, I think we can go ahead. So the company actually, there were various ideas around what the company would be doing at that stage, right? It wasn't like what you see on the screen today where there's a motorcycle, and this is sort of the eventual completion of that goal. But at that stage, we had very humble beginnings. And what we were looking at was, we were looking at the success of various companies in the space. It was starting to become very clear and apparent that electric vehicles are going to happen, right? It was no longer a question of, is it going to be hydrogen vehicles? Sort of those questions were getting answered already, right? It was that the electrical grid itself is 85-90% efficient at transferring energy from the source to the last mile, and electric vehicles are just plugging into that grid, right? And it was very clear that no other sort of form of energy can meet that kind of distribution, and electric vehicles are going to happen no matter what people want, right? And what we started to see is that there are many opportunities, from four-wheelers to, you know, three-wheelers, two-wheelers, and a lot of companies were trying to solve problems, but there were some very difficult problems which, if solved, could be very valuable to the future of electric vehicles, right? And that was around particularly performance, high-end two-wheelers. It's also quite exciting for us. We saw a lot of companies trying to build, you know, low-powered scooters, and there were enough companies attempting that, and we saw that that would succeed. There was no question about cars. There was no question about scooters. There was no question about, you know, three-wheelers, commercial vehicles. But one of the things that we saw lacking at the time was that if people have to take electric vehicles seriously, how are they going to get vehicles that outcompete IC engine powered vehicles, right? Where are the motorcycles that people love and crave, right? And that was the starting point for looking at this particular segment and deciding that we are going to focus on this segment. Of course, it involved more than a year or year and a half of, you know, background research, which I will get into a little later, in terms of the kind of work that we did with potential customers, with sort of user research related stuff. But that was the starting point for everything. Now, before I get into some technical detail, like I was talking about how today the vehicle is sort of production ready, and, you know, as we're preparing to launch the vehicle into the market, it appears all glamorous, but that's not where it all started, right? It all started in one tiny room in Koramangala in Bangalore, on the terrace of a building, right? There was just enough space for like a few people to walk around. It started with some computers and a 3D printer. And this was the first office, so to speak, of Ultraviolet, right? Where I don't think even 5 people could be seated there. There was only hardware everywhere. There were ideas about prototypes, about what we would build, but essentially we quickly grew out of that space. As we did a lot of user research, as we started to build prototypes, we needed a larger space. And the second sort of office space that we took up, you see some part of the bike there. That was one of our first prototypes. You see the team. When we moved into the space, we were a few people, I think less than 5 people, and this felt like a massive space. Why do we need so much space, right? But towards the end of the second year, while we were there, this place had about 20 people, and there was no longer a place for people to walk around, right? So this was our second office, right? Today, the office that we operate out of, where I'm sitting in today, is this building. And it's been a long way from, where we started, which was sort of a tiny room in Kormangla, to where we are today, where we have entire prototyping, mechanical assembly, mechanical design, electrical design, battery engineering. All of this is happening here today. And if you told me 3 years ago when we moved into the space that we may be running out of space at this place, I would have laughed it off. But now, today where I am, I think in the next 1 year or 1.5 years, we are going to run out of space here as the team sort of scales up. And frankly, it's been quite a journey to get to where we are. Now, all of the things that I'm going to be talking about now actually haven't been, done by a small team. It actually takes a lot of effort. It takes a larger engineering team, a larger design team. So what you see on the screen is actually a team that, this is actually a photo from pre-COVID times where people could stand close to each other. But essentially, this is a team from where the sort of company started scaling into going towards production, right? And we've been very particular about the folks that join us. The reason being that while it is good to be, sort of young and ambitious, it is also important that people come with the skills that it takes to build what will be the final product, right? So the team that we have today typically comprises of people from 3 domains. One from the automotive engineering domain, one from the consumer electronics side, and the third from the aerospace engineering side. And this is important because this is what actually differentiates us from the typical OEMs, as they're called, the large automotive companies in India, because the skills that are required to make this kind of vehicle, this kind of electronics, very high tech, very quick in terms of innovation and cycles, comes from other industries like consumer electronics and the aerospace side, where simulation is very important. So both on the mechanical engineering and on the electrical systems, the electronic systems, the software development side, all of those, actually the skills that are stronger come from the other companies which are not from the automotive side, right? But at the same time, we need to work with the industry to create vehicles, and we need to work with automotive companies in that space, and that's where the automotive sort of DNA comes in. So the DNA of all of these 3 different domains and industries actually comes together to create Ultraviolet as we know it today, right? Let me just look at any message requests. Okay.
There are a few questions, Niraj.
Okay.
Do you want to answer this now? Probably.
Okay. Yes, I think I'll quickly have a look. So did you have access to drones and the electronics way back before 2010? Yes. So actually what we would do is we would go to websites like Tower Hobbies, Hobby King, and we would order, it was very expensive back then. There was the same problems around customs duties, things getting stuck in customs, but we would all pool together money, buy particular hardware, lithium-ion batteries, lithium polymer batteries, different flight controllers, different kinds of speed controllers, motors, and that's where it all started actually. Even how do you evaluate which motor would work for which particular drone size, what would be the payload of this drone. So that's where it all started actually, and we actually had access to hardware. Of course, it was expensive, which meant that we would have to try and raise money for it through sponsors or through parents or family or friends. So that's what sort of came together. Some other questions?
We can probably select a few.
Yes.
You're running out of time. The next question is, these days, starting up automotive space is quite challenging unless there is a massive backup.
Right.
So how did you manage to get there?
I think at every stage, there is a requirement for capital. There's no denying that. But at the same time, with whatever resources that we had available, we would make progress. So at any point when investors would come and sort of meet us, they would be surprised by how did these guys who don't have access to all of the resources that a large company would have, how do they reach this stage? How do they build a prototype that is faster than all 200, 300 cc motorcycles with a few, like, it wasn't even significant, the funding back then. How did these guys recruit and build a team that is so capable and strong without being a large company, right? So it was things like this that along the way, whatever few unfair advantages that we had to use them to build the company. And that's when the capital actually came in. So it wasn't that, okay, you go with a business plan on a presentation and then people are going to give you money or you can raise money. That wasn't how it was, right?
Mm-hmm.
I hope that answers the question to some level.
Yeah, yes, it does. There are other questions as well, guys. What I can do is because we have like a lot to cover as well. So what I can do is I can get all these questions, send it to Niraj, and probably Sweta can send the answers back whenever Niraj finds time. You can probably answer it offline, and we can share the answers to all the attendees right after the session.
Sure. Okay. Sounds good. Sounds good. Okay. So let's move ahead with the presentation. I think now let's come to sort of the real meat of what we're talking about here today, right? So it's taken about 5 years to get to where we are. The final product is sort of almost here. But there's a lot of work that has gone into it. And now what I'm going to be talking about is actually the process that we have gone through to build the hardware that I'm talking about, right? And just keep in mind that it has taken several dozens of professionals from different domains to do all of this. It has taken several years to build this process. It has taken, not all of these steps were always followed. Some of them have been done later. Some of them have been done earlier. It has taken over 7 iterations on the product design to get to this stage. But essentially what we have now built is the capability to build the hardware that you see on the screen, right? And it all starts at a very early stage with, the very notion of what do you want to build, right? This goes back to consumer research, market research, and I will sort of limit the amount of textual information on the screen. So these will be one of the only few slides with so much text on the screen. And I've kept it more visual in nature, but it's important to understand that defining at a very early stage what needs to be built is very critical to the success of the product, right? Which means that understanding what the customer requires, understanding not just performance or functional requirements, it has more to do with lifestyle choices, aspirational requirements, price points. All of that information has to be done at a very early stage before anything can be sort of even conceptualized. And this is what happened at the very early stages, I would say 2015, 2000, most of 2016, before we started work on the vehicle itself, right? From user profiling, market research, storyboards, we would build some very early stage concepts. So all of these things that you see on the screen, I will give you examples of that. I will talk about it in some more detail, but this is sort of the early stage of defining the requirements. And there's a stage that comes after this as well, right? Which I sort of call as design in terms of the stage 2, right? Which is now it is sort of becoming narrower and narrower. Now you've thought about it, you want to build a motorcycle and it should be capable of withstanding Indian road conditions. It should be capable of doing this kind of maximum power. It should be capable of accelerating from 0 to 60 in this time. It should be capable of this top speed. Now, there are also other requirements that the vehicle should not be priced, more than what people are used to paying today for motorcycles. There are certain regulatory requirements for these vehicles to be sold in India and in different countries. There are usability requirements from, people are used to riding motorcycles of a particular type. You can't drastically change that as well. So these are all being sort of coming into the requirements, and while on the screen they may be visible as simple, bullet points, these are extensive documents that are created, because later on when you finally build the product, you are sort of also going to be validating that is this product meeting the requirement that I set out to achieve, right? Can this vehicle withstand 100,000 kilometers or 200,000 kilometers on the road? Can this vehicle withstand the Indian conditions in terms of temperatures, in terms of operating conditions, in terms of water, right? So all of this is being sort of included at a very early stage, and it's important to get this right. And the problem with doing this is that you're trying to forecast what would be the requirements 5 years out, 7 years out, 10 years out, right? And often there are a lot of constraints that you don't know about. Like you don't know how the industry is going to evolve. You don't know which charging standard is going to happen, right? So there are lots of unknowns, lots of questions, but you still have to build and progress. And there are certain requirements that will change. And hopefully the requirements don't change so drastically that you have to redo your product from scratch. But the unfortunate reality is that the requirements, especially if you're talking about a product development cycle that spans a few years, will change over time because of the climate, because of the sort of market, the market conditions, the climate, for various reasons, right? Now, once these sort of requirements get defined, that's when we go into sort of what is a pre-design stage. These are very early stage, low fidelity prototypes, both on the mechanical side, conceptual designs, prototypes, what you'd see later on in terms of clay models. On the electronic side, these would be, you use standard development boards. You start, you don't have your own custom hardware. You're using evaluation kits, reference boards, and starting to sort of build the software as well for that while you're building your own custom hardware. So this is at a very early stage, checking for feasibility, checking for, but you're starting to think through what is the final product going to be. And on the prototyping side, you also have to deal with hardware, which means you're prototyping with metals, with plastics, sort of all of these things coming together. And the processes that you use for prototyping doesn't really apply to the final product also, right? When you go for plastics, for example, you do 3D printing, which can't work for functional parts, it's just for aesthetic parts. You use, different types of vacuum casting, which again does not scale into production volumes, but it is essential to evaluate products at a very early stage. So these are sort of the early design requirements. And just to get into some more detail about what this means, right? As far back as I can remember, one of the most important steps that we had to sort of do was evaluate if a particular kind of rider who's going to buy this vehicle has to ride this vehicle, what are they used to, right? So we had to go into the research on ergonomics, understand in detail. So this is what is called the rider triangle, right? And for different motorcycles, this is the kind of behavior that they're used to. This is the kind of performance that they're used to. This is the kind of usability requirements that they're used to. And so all of this gets captured in a very tabular, detailed way. What I sort of mentioned earlier is I'm going to use visual aids to sort of explain what I'm talking about, because, this conveys the message, I think, better than just tables of, dimensions and weights and center of gravity and these kinds of things. But the idea here is we had to understand what is it that the market is used to and what is the expectation of a future product. And this is where it all starts, right? While we may have a notion that we want to build a very cool high-tech product, you still have to understand what is it the customer is already using today. And this is where it all starts. Then comes, very early concepts. Now you're drawing on paper. And this is again very interesting from a perspective of an engineer, right? So today, from my background in the past, etc., we are used to finding functional solutions for problems, but there's an element of creativity that we don't get to always see. And this is where I have been exposed to the designers from industrial design, automotive design, that it is very important that the product that you're building is also sort of something that people want. There is an aspirational value to it. There is a sort of aesthetic value to it, all of which is critical and sort of merges together with the functional requirements. And it's sort of where art meets engineering. And it all starts with sketches on paper like this, right? And at this stage, there's frankly very little in terms of, 3D models or anything of that sort, right? So it is just purely sketches on paper, and there are hundreds and hundreds of explorations that happen at this stage. So I remember actually Narayan and the team working on, so many concepts that they would tear down ideas every day. They would combine ideas every day. And these are actually initial sketches from the concept explorations very early on. I'm talking about 2015, 2016, where, once you've defined that this is what we want to be doing, these are various ideas that are going about and being discarded dozens of times, right? And at this stage, it is very hard to get you've built a sort of concept on 2D on paper, but that is still insufficient information to determine whether this can actually scale into the real world. So what we do at this time is also we start building rough 3D models of particular products. So these are very rough. We don't get into full detailed design, and we sort of do an analysis of this in virtual reality, because now you can actually walk around the vehicle, right? You can actually get a sense of what is the scale, what is the proportion, how would different lighting affect the different surfaces of the vehicle, how does it look in different types of lighting, the colors, right? There's still a lot left to be done, but at this stage, what happens is that you start to realize that there are inconsistencies in your design. You've built a 2D model of something on paper, but when you build it into 3D, you realize that some of the things that you thought were possible are not really possible. It looks from a particular angle, from a particular direction, from a particular perspective, that things are not what they seem, right? And so it means going back to the drawing board. It means going back to, the conceptual level again, and sort of redoing from scratch what you want out of the vehicle, right? It means changing a lot of things on the frame, changing a lot of things on, the concept itself, refining the concept to a stage where, okay, these are the ideas that we have to discard. These are things that we can't take forward. This does not look realistic. So it goes back. And if you notice, there are, in terms of technology, in terms of engineering, there's still, I would say, some aspects of it, but at this stage, it's very creative, the process, right? You're spending time, if you look at the design of the vehicle, it's about how different surfaces come together, how this concept is being refined. And while there is already development starting on the electronic side, on the battery aspects of it, I can't really talk about all of these things in parallel. So I'm just talking about from a mechanical design perspective, what are the things that would be happening, right? So these are refinements. Again, you go back into VR, you explore some of these concepts. And once you it is decided that, this is a particular concept that we want to take up, that's when the next phase of building something real sort of happens, right? And this is where the clay models start to happen. And this is usually, again, this is a few months in terms of the time frame. These are hand sculpted clay models, which sort of give you a sense. Now you can even sit on this vehicle. It's not really a vehicle, but you can sit on it. You can get a sense of the ergonomics. You can get a sense of the proportions. And it has gone beyond, a virtual reality setup, which means that there is touch and feel involved. Of course, these are not the final materials that go into the vehicle itself, but these are, giving you an actual real world representation of what the vehicle could possibly be. So for example, what you see on the back there on the wall was the poster, which was the inspiration for, building out this clay model. And there was a lot of work, months of effort done to sort of get it to that stage. There were rough 3D models of the same vehicle, and then there were clay models of this as well, right? And when we talk about 3D models, this is where we're getting into, each of the particular parts, from the single footrest mount to the mirrors, to all of this is being detailed out in 3D, right? And you're going back and forth between clay models, between 3D models. And we reach a stage at which point, most of the designers are happy. And it takes a while to get to that level of happiness, because frankly, there will always be things that can improve beyond a point, but then there are time constraints as well, right? So you want to finalize the aesthetic design of the vehicle, the form, and now you're sort of starting to get into the function of the vehicle. And that gets into detailed sort of 3D design. You're going into the frame of the vehicle, you're going into every aspect of engineering, and sort of building out even the smallest fixtures, just building out the mount points, all of that in a lot of detail, right? And so far, I've just only spoken about, the mechanical engineering aspects of the vehicle. I haven't really touched upon, the electronics, the software, all of those aspects. And so while all of this is happening, actually there is work already going on in terms of the electronics, right? So what does that mean, right? So it sort of means that you're starting to define your system architecture, you're starting to define your constraints in terms of mechanical, that the PCB cannot be more than this dimension, right? You're starting to make schematics, which are sort of more detailed block diagrams for those from a different industry. You're starting to define how every sort of electronic component on the final PCB would function, how would the interactions be with different other components on the system. You're starting to get into bill of materials. You're getting into understanding what kinds of microcontrollers you need, what kind of processing you need, what are the capabilities in terms of accuracy, in terms of sensitivity, in terms of power consumption. All of these things are getting defined as the constraints, right? And that's when the final outcome is sort of a schematic that is released. And then we go into what is sort of a PCB and layout redesign, right? So again, this is another area where I would say that it's a combination of both art and engineering and science, right? Because different PCBs are designed differently by different individuals based on their previous experience. So what started as a schematic, something like a document that you see on the left, which runs into 30 pages. I've taken a snapshot of one part of one page, goes into the actual layout design of a PCB, right? And what does that mean, right? So it means that first you start from the point of your placement design, right? Where are all of these different components going to be placed? Where is it? How are you sort of defining the copper traces that go along to different parts of the PCB? What are the different layers that are there within the PCB? What are the other constraints that are there within the dimensions of the PCB that you can accomplish? How many layers do you need? And that sort of also defines the cost of all of this, right? If you build a 2-layer PCB versus a 8 or 10 layer, that increases the cost. So all of this, then you design how is it that you're going to, this PCB is going to be part of a larger manufacturing process, which means that can you generate 10 PCBs out of a single, larger board? And we go into things like placement reviews, routing, layout reviews. And this is again a very, very specific niche skill set that at the early stages, some of the folks who would work on the schematic itself would build it out for themselves. But as the company began to grow in size, we would need experts, right, who have worked on this for several years or tens of years, and they would sort of work on this. And again, there's a stage that comes after this, which is around simulation, around analysis, which I will get to in a bit. But once you sort of have this in place, you start planning out prototypes, right, of electronic devices also, which means that you're building very low fidelity for prototypes, which means that it could sometimes mean that you're not using the final hardware, you're using what could be a reference design, a reference board. You're trying to use those components from, a company like Texas Instruments or ST Micro, and using their development boards and sort of prototyping your electronics, the battery packs, the vehicle control units. You're doing board bring up, you're doing board assembly, you're creating sort of all of these bare bones electronic systems, and you're starting to plan out even the software implementation for all of these, right? So this is what is happening at a very early stage when it comes to the electronic side of things. Jumping back into a little bit on the mechanical side. So this is where mechanical and electronics are starting to come together now. You're starting to think about, a vehicle as a whole. You're trying to see that, okay, how would this PCB fit into this vehicle? Where would the batteries fit? Where would, what are the constraints for both the mechanical side? And now at this point, it's usually the electronics team that is pushing back on the mechanical team, saying that, I need so much more space. I need a few millimeters more or a few inches more. And the mechanical team, there's a lot of back and forth that happens in this phase as well, right? So this is more detailed design while you're doing prototyping, and there's back and forth. You realize, okay, this is not going to work. This is insufficient to meet one of the team's constraints. And so there's a lot of back and forth that happens. And you go into every single components. How do the components interact with each other? What are the possible failures that can occur at each stage? What are the interactions that happen at each stage? So this is what it actually looks like, right? So day-to-day work is not always very glamorous, but it's very thorough, it's very detailed. And you have different types of systems interacting with each other. You have different types of constraints from each of these systems, and they're all coming together as part of, and it's important to build this documentation and base, because later on you would want to know why a particular decision was taken, and how, if you change that particular decision, how everything else is going to change. So a lot of this is actually what day-to-day sort of looks like, right? And while all of this is happening, as we are progressing towards the design, there's a very important phase that we get into, which is around simulation and analysis. Now, usually before we build any high fidelity prototypes, which means that the prototype is intended to function as very close to the final product, we go through a round of sort of simulation, which is both on electrical side, on the mechanical side, on structural aspects, on thermal, on aerodynamic aspects, and sort of at a very high level, again using visual aids. If you can all see my screen, what you see on the screen is actually a lot of simulation and analysis that happens while we're building different types. Right now, what you see on the screen is mostly electronics related, battery packs related, which is you do all kinds of power integrity analysis, current density, voltage drops across PCBs, how your thermals are affected. Like if when you're drawing power from cells, there's a tendency for the cells at the center to heat up more than the ones at the sides, right, at the corners. How do you eventually cool these cells? What is the temperature difference that is expected to happen between the centermost cell and the ones on the side? What are the what is going to be the power consumption of a particular PCB? Where is the heat going to be dissipated? How is that heat going to be released to the outside world? And so this is from a sort of circuit simulation, your analogs, how is your digital signals going to perform on the PCB? So all of this simulation is happening on the electronic side. And on the mechanical side, there's also sort of, you start to look at the structural integrity of things. So what you see, for example, on the right, at the bottom right, is a battery pack which is being simulated to be dropped on a particular corner or edge, or these kinds of things. And then this also happens at a vehicle level, right? So if we talk about the frame of the vehicle, now the frame of the vehicle is intended to work on Indian roads, right? Which means that it has to be able to withstand particular kinds of stresses, strains, impact, right? Now, and while there's one way to build it, which is that you sort of look at other benchmarks and build out the vehicle, that is usually insufficient if your time is your constraint. The problem in sort of not doing this kind of important simulation, which is sort of also time consuming, is that you build a prototype, you spend several months and you try to take it out and it fails. So we would prefer if the failures happen in software. We would prefer if the failures happen in simulation. So you sort of build this confidence, to a level 90%, 99% sort of confidence before you build out a prototype, or a high fidelity prototype, as we would call it, right? So this is what is happening on the structural side of things. And this also happens for a combination of electrical and mechanical components, right? You have things like vibration and shock requirements for your PCBs, you have thermal requirements. So all of this is sort of coming together. So what you see on the right is, I think, deformation when under different scenarios, right? So the frame undergoes deformation from different perspectives if it goes on a bump versus if there's a person sitting on the pillion seat of the vehicle, right? So there are different requirements that come in from a simulation perspective, and all of this happens. So I'm showing you a simplified sort of model of simulation, but if you actually get into the entire vehicle, it's a lot of work, because every single part of the vehicle undergoes this kind of simulation. From a single gear inside the gearbox to the gear tooth itself, how much work goes into defining the constraints for that particular region, right? So the front shock absorbers, the front fork, the wheels itself. So all of these are custom designed parts, and there's a lot of work going on to validate that each of these would actually make sense in the real world, in the field itself, right? And now the other questions that we typically get asked when it comes to simulation is, how close is it to the real world, right? And usually it depends on how, and it's a good question, because frankly, when you do your simulation, you're making certain assumptions about materials, about metals, about the process that you're using to manufacture these materials, whether it's the swing arm, whether it's the frame of the vehicle. And real world prototypes actually differ to some extent on the materials used. So from a particular manufacturer in some part of India, you don't get what is promised or what is assumed on your software side, right? So while it is important to do these analysis, it is also important to verify them in the real world. And that's the other loop that we get into as well, right? And that can only happen once you build a prototype. right? So it's a lot of back and forth that happens, which is why when I talk about it right now, it seems like everything makes sense, looking backwards in time. But when we actually started doing all of this, it wasn't so obvious. Like, do you build a prototype first, or do you get into entire simulation to some level? And if your simulation doesn't have enough background data on materials, like how are you going to do that simulation? Where are you going to collect road data from, right? What is the worst kind of pothole that this vehicle will encounter? So how you either come up with some notional idea about what the real world is going to be and simulate that, or you try and build prototypes, get some data, and again go back and simulate. So there are various loops of this that happen when we're designing the structures on the vehicle, right? Going into some more detail, this is more on the CFD side, fluid dynamics, thermals. So a lot of what we do again goes back to battery packs, how the battery packs are cooled. The most important aspects in an electric vehicle, which are complete unknowns because this is a new field, relate to the batteries and the electronics, right? So the questions become around, and one of the most basic fundamental things around batteries that we have seen from the last 15 years is the batteries are very sort of sensitive to operating temperatures, right? There's a very narrow range in terms of temperatures that the batteries can operate with. And as and when you push them towards extreme ends of temperature, you start to see degradation happen faster, right? And you start to see performance degradation. And within a battery pack, if a single set of cells or single row of cells or even a single cell starts to degrade faster than the other cells, now that is becoming sort of a single point of failure for the entire battery pack. And so while cell phones today, while we have our cell phones which have a single cell, we're talking about vehicles which have hundreds of cells, right? And you've seen how even your phones tend to heat up when there's extensive usage, when you're gaming, when the screen is on for a long time. Now imagine much higher power requirements and hundreds of cells coming together in a vehicle, and how they would have to behave for it to make sense, right? You have to be able to cool these batteries, cool these cells to a point where they are even, and have to build predictability into how they degrade over time. So a lot of the work that is done is actually around these lines as well. The same goes for electronics, right? So while current is being discharged, current is flowing around copper parts on the PCBs itself, it tends to heat up because there is some internal resistance or impedance as part of the design itself. And how do you dissipate that heat to a point, or manage that heat such that for the worst conditions the temperature rises less than 20 degrees or less than 30 degrees, right? So these are the constraints that get defined, and when you build a prototype, you actually have to measure this and check it, right? Then comes the aerodynamic analysis on the vehicle itself. Now one of the things that we have to do is that this is meant to be a sports motorcycle. It's meant to sort of compete with IC engine vehicles, etc. So how do you build a vehicle that has low aerodynamic drag, and at the same time you want to cool certain parts of the vehicle? So whatever drag is there on the vehicle should ideally be used to remove heat from the vehicle. So how do you manage that? So what you see on the screen is actually just the outer surface, but there's a lot of work that happens on the inside as well, right? To redirect and channelize air into the vehicle, to cool the batteries, to cool the vehicle electronics, to cool the motors. And just to give you a perspective of how that happens also. So for example, what you see on the screen actually...
Niraj, we have a lot of questions. Do you want to pause and then answer these questions, or how do you want to take this?
I would want to pause and answer them.
Sure.
Next. So
I'm going to ask questions that are top voted. The first question is, was the decision to retain a fuel tankish structure in the product's final form factor is to do with ergonomics or avoid cultural shock?
Okay, that's a great question. Actually, yes, that's an amazing question, but the answer actually has been answered by the person themselves. Like, there are both of these reasons, right? So if you notice from an ergonomics point of view, if you ride a scooter, which you don't have anywhere to keep your legs, to wrap your legs around, right? You will notice that you can't make very drastic dynamic decisions when you're riding a scooter, because frankly you are floating on that seat above, right? You're not really well attached to the vehicle itself. But on a motorcycle, when you wrap your legs around this, and if you notice a lot of professional riders, race riders, etc., when they're cornering, all of their weight is actually placed by their knees, by their upper thighs on the frame of the vehicle, on the plastics near the fuel tank area. And so it is very critical. And how that improves the whole system is that now the person and the vehicle have become sort of one. It's not that a person is floating above the vehicle like in most scooters. It is the person is very tightly coupled to the vehicle, and you're able to make dynamic changes as and when you move around, as and when you're cornering, and all of that has to do with how your sort of legs sort of interact with the vehicle. It's not that your only 2 points of contact are the foot pegs, right? It is actually it's way more complex than that. You're leaning in, and the entire force and pressure that you exert on the vehicle is through the entire leg and not just your foot pegs. So the ergonomic design does require you to have a very stable position, especially for dynamic situations, right? You're leaning into a corner, or you're making drastic changes in direction of the motorcycle, and all of those can be better accomplished if the person is better coupled to the vehicle, right? The second aspect of this is also history, right? There is a certain value associated with motorcycles, and there's a particular design that if you tend to go completely away from it, and we have done some of these. I have not shared those images with you at a conceptual level. At a conceptual level, when we design stuff, there is the complete freedom to go completely wild, right? Which means that it may not even look like a motorcycle that you've ever seen before, not even in the most futuristic science fiction movies. But then there's a hint of reality that needs to be added to this, because you are selling to the real world audience. So you can't make something that is so outrageous and ahead of its time or out of its time that people are going to question, what is this, right? You don't want that experience to come about. So it's a combination of both. And that was actually a great question there.
Yeah, it's a really good question as well. So next question is, are the electronics and hardware, including the 27 kVh motor, are built locally for UV or outsourced from international markets?
Okay, that's a great question again. So we take several decisions along the way. Let me put it from this perspective. The way that I see it, by the time the vehicle is in production, a year from now, all the vehicles are rolling out in the market. There are hundreds and thousands of these vehicles being built up. The only external dependencies that we would have outside of India would be on two fronts. One would be the high energy density cells that come from typically Japan or Korea or those countries. And the second is on the magnets that go within the motors. The rare earth elements that are required for these magnets are found in certain concentrated regions around the world, right? And so the neodymium magnets, for example, which are very high magnetic flux density, those are the ones that would come from outside India. But the good part here is that the rest of the vehicle, right, everything else, there's a very good supply chain in India. So the reason for that is that India actually is a very, very evolved market for two-wheelers when it comes to comparing it to the rest of the world. The large companies that have existed in India over the decades have built this extensive partner and supplier network. So for every metal part, every plastic part, there is enough and more suppliers in India. And even on the electronic side, the good part is a lot of the electronics for global companies is actually manufactured here in India, in and around, for example, Electronic City in Bangalore itself, right? So large companies, including the Bosch Continental of the world, all manufacture their products out here. So the good part is that a lot of this is actually available in India. The two components that I mentioned, the magnets and the cells, we do see that over a 5 or a 10-year period that these would be manufactured locally as well. For example, the government of India has set up a rare earth mining institute and an organization in Visakhapatnam. I think they are going to be producing the magnetic material that is required for magnets in India, but it's probably a few years away the way I would see it, right? So that is just on magnets. And for cells, again, we've seen that there's been technology transfer agreements from companies like or organizations like the Vikram Sarabhai Space Center, the Space Research Organization. And so it's going to take a couple of years. There are lots of international companies setting up production plants in India for cells. So all of this is going to happen over a period of time. And the way I see it is in a 5-year or 10-year period, like everything would be completely localized and there would be no external dependency whatsoever. I hope that answers the question.
Yeah, absolutely. Thank you. So the next question is about, a new question, but top voted as well, right? How ready is the manufacturing ecosystem to build at this scale? How do you plan to collaborate or compete with the likes of Ola, which is launching a large-scale manufacturing facility soon?
Again, great question. So the good part here is that, see, we don't manufacture every single component. There's a very strong supply network, right? So what you see, for example, the front fork, we design the custom components. We work with the manufacturers to define the constraints in terms of what materials, how would they all come together. We work with them in terms of process engineering, the development engineering, as to how the mold flow analysis, things like that. But finally, when it comes to manufacturing these parts, most of these companies actually manufacture parts for all of the OEMs. So it's the same guy who would be doing this for us, and they would be doing it at a different scale, smaller or larger for another company, whether it's the plastics or the metals, right? And for us, we don't see that as a sort of an issue. It is more about which kind of product requires what kind of scaling. And we work with different partners when it comes to manufacturing these parts. And for us, it's sort of, we are planning out our assembly facilities. We're in discussion with various governments in South India. So in terms of where do we facilitate and create our plant, which is where it all comes together. The final integration happens, the final checks and balances, the testing, the verification happens before the vehicles are rolled off the assembly line, right? So that's where it all comes together. But at different scales, different companies will operate, but they all work with the same ecosystem, right? So the look and feel of the product may be different, but the plastics that are manufactured would probably come from the same company in South India, right? So that's how this whole ecosystem operates.
Great. So we'll probably answer 3 more questions.
Sure.
The next one is, what is the level of modularity that has been built into the system, given the fact that there are so many external protocols that could change from charging tech to whatnot? Has the product been divided into small functional modules?
Again, great question, because this is a constraint that we set ourselves up with at the very early stages, right? So when we talk about the requirements, both on a mechanical and an electrical system side, you have to sort of decouple different components and create interfaces between them. And these cannot be too tightly coupled, which would mean that if there is a change in a business requirement or a functional requirement that this product go into a higher category, higher power level or slightly lower power level, it should not completely break the system. You should be able to reuse that existing component. You should be able to use the same architectural standard to sort of build for a changing or a variant or a new vehicle segment. So while this actually makes things a lot more complex at the early stage, which means that now you've added the burden on yourself, right? You've created a new interface requirement. You've tried to loosely couple 2 different systems, whether it's a mechanical system or an electrical system. And there are so many unknowns, whether it's the charging standard, it's the communication standard. It's difficult to actually deal with it. But what typically tends to happen is that if you've built in this modularity at the very early stage, that helps later on. So for example, we've taken 4 years to get to this stage where the vehicle is production ready. Now, the good stuff is that once we launch this vehicle, the next vehicle, or which may be in the same segment, a different segment, a variant with a different capacity, or all of these things, right? That will not take more than a year. I would say from anywhere from 8 to 12 months, because we have built in the modularity both on the mechanical side, on the technology, on the electronic side, on the software side. So all of that modularity is already built in, and that made things harder for us, but it was necessary because the constraints were not defined in the market itself, right? The market itself was evolving, so we had to keep those constraints.
Great, thank you, Niraj. So the next one is, What goals did you set for your teams along the way in the absence of revenue sales goals to keep the team going? And how do you determine product timeline goals?
Again, great questions. So I think, can you repeat the second part of the question? I got the revenue goals, etc. What was the second part?
How do you determine product timeline goals? Because there is no financial or revenue goal, right? So
Right,
how do
right,
you
great.
that?
Okay, yeah, yeah. Okay, so see, I think first is when it comes to R&D, at such an early stage, it's very hard to sort of put a profitability metric right on in terms of the R&D team itself. It's not, I would say, a business unit, because the lag time, or it's a very long lead time, right? That from the point of that this vehicle is being designed to the final product, that we can sort of plan what is going to be the business unit and what is the profitability of that particular business unit, etc. So the way that we operate is actually work backwards from the requirement, right? This is a particular segment of motorcycles where anywhere from 80,000 to 200,000 vehicles sell every month, right? And of course, we are not going to be able to sell that kind of volume every month when we start off, but that is the market that is available. Now, if we were to achieve distribution, 100% distribution in all of these areas, we would probably come close to a few percentage points out of that market. And now we work backwards from there. We know the market, what is the total addressable market, what is it that we can sort of look at in the first few years, what is it that would be the price point of these vehicles, and that is a very important factor while sort of building out the vehicles, right? So you say that for the company to be sustainable, this is what the vehicle should cost in the market, and this is what it should cost for the company itself to build. And now you've defined a target price, and now backwards from there you start to build out that's what you see, a bill of material constraints on the screen, right? So each particular part of the vehicle, whether it's the frame, the plastics, the wheels, the electronics, all of them have to come together and fit into this final product cost, and it has to make sense for the business as a whole. It has to be sustainable for the company, which means that there's a lot of back and forth, and you start to realize that there are constraints everywhere along the way, that a certain part, for example, it would be great to have carbon fiber on our motorcycles, right? But if you look at the cost of carbon fiber, and if you look at the price point that we're trying to make this motorcycle available at, those two don't match. So we have to look at more reasonable means of producing the vehicle. Carbon fiber today is not a material that you can consider for this kind of scale that we're talking about. There's a lot of back and forth. For some parts, for example, you don't have a target price, right? You don't know. Electronics, batteries, the prices are changing. So then you work, bottom up. You say that if we were to use this particular design, this is what it would cost. And then you merge together all of this data to come up with a whole overall model, which is the overall bill of materials of the vehicle, and say that this is what it looks like, and this is what can make sense for the market, right? So it's a lot of back and forth. In terms of timelines, now again, this is a great question. So this is much harder to do, right? You can't say that, it can't be unrealistic goals. You say that, okay, I want to build a motorcycle in 6 months. Now, that's one way to do it, but then the entire team would be like, this is ridiculous, right? And we've seen that happen in a lot of companies. So the way that this timeline also works is both a top-down and a bottom-up approach, and it's where it all meets together in the middle. So there are certain business requirements that you need to be able to launch a product in X years, right? And at the same time, there's a certain development timeline. So senior engineers, architects, principal engineers all come together, give their opinion on what is a realistic timeline, and we try to find a middle ground in terms of what is possible with the resources and constraints that we have, and what is the realistic development timeline. And it does change over time. There are constraints. There is COVID, which came about and changed the whole industry for everyone. But those are sort of more unknowns, more variables that you add to the mix. But as much information as possible from both sides, from the business side as well as from the technical side, come together to sort of create these timelines so that it is as far as possible realistic, and we try to meet them. And then you sort of add buffers into all of this to account for any variances, changes in conditions, right? So all of that comes together.
So great, Niraj. Yeah, one more question, fairly easy one, before jumping into the presentation. Which mechanical design softwares are being used to make the bike models?
I mean, there's a whole suite of softwares that are used, right? I won't take particular names too much because, these tend to change over time. There tends to be a lot of, what happens is that some of these software become outdated. So our team learns to use some new software. But these are the standard softwares like SolidWorks, things like that. Engineering, it varies based on a personal skill set point of view. So there are various softwares involved over there, from the surface design to detailed 3D models to simulation to the PCB design to electronic simulation. So there are various softwares involved there. I would not place too much emphasis on that because I've noticed that when we talk about certain softwares, that sort of tends to set a particular direction. People think that that is what must be used, but that is not true. What we sort of focus on is more fundamental aspects, which is that the physics of it, the math behind all of these simulations, or the process, it should be independent of the software. The software is just a means to an end, right? But what we're trying to do actually should be possible with different kinds of software. So we don't particularly restrict ourselves to any one software. So even when we talk about using a particular tool, we also are constantly experimenting with other tools, whether it's open source or a different vendor at a smaller scale, to see if this is what the next generation of software would be like. So we're very open and flexible around these things.
Thank you, Niraj. Yeah, we can continue with the presentation. There are a few questions. I will moderate that as well. If we have time, we'll try to answer the questions, or we can do it offline. Thank you.
So Dinesh, just give me a sense of the time check. Like, what are we now? How much time?
We are at 11:20. We can probably do it for like 20 minutes, 15-20 minutes more.
Okay, sure. Got it. Thank you, Dinesh. Okay, sure. So I think I'll come back to where I dropped off, which is, we were talking about how aerodynamics of the vehicle, how it all comes together in terms of the design of the vehicle itself. So again, what happens is when you're at a simulation stage, you may have to go all the way back to a concept stage, right? And this is one of those examples where you sort of make a particular design in terms of the air vents on the vehicle. This is what appears behind the front wheel of the vehicle, and there are certain concepts and exploratory concepts that we make, and then it goes into simulation. And then what happens is you realize whether a particular simulation results in airflow to the batteries, to the motors, to the electronics, whether it improves it or it hinders it, right? And you sort of see how it affects the electronics, how it affects the cooling of different systems, and then you may have to go back and change the concept there. But again, this goes back to some of the questions that were there earlier as to how do you define modularity, right? So now, just because this part of the vehicle changed does not mean that the rest of the vehicle completely changes, right? So we have decoupled this front section behind the front wheel just to deal with the aerodynamics, but you made sure that the rest of the vehicle is not impacted. So it goes back and forth, and before the design can be finalized, it's a lot of work that actually happens. But this is how we arrive at what would be, the final solution itself. And, going into a little bit of a later stage process, once we start to sort of build all of these things together, once we start to prototype all of this, we start to sort of bring together all of these different components in terms of designing for manufacture and assembly, right? So what do I mean by that, right? So when we talk about design for manufacture and assembly, it's about, standardizing components. It's about verifying that this is possible from this particular supplier or manufacturer. It's about how all of these different components stack up together. Each of these components have different tolerances, right? So once you start putting together all of these and integrating this, you notice that if there's a 0.1 millimeter gap between two components, or and that starts to vary, then things start to rub against each other, or there are variations that are possible because of the manufacturing process. So all of these need to be accounted for, and you do a sort of design for manufacture back and forth with the supplier, back and forth with the constraints that are available to you. And sort of once the prototypes are there, you start assembling together and seeing whether they make sense, whether they stack up to what was your original design. And there's also another part of this, which is the design for assembly process, right? Which means that if you look at a mechanical, just set aside the motorcycle for a bit. If you look at any particular laptop or phone or any hardware device, you usually build certain components for particular types of access and assembly. Like your laptop, you may change a particular part of the laptop more frequently, like a keyboard or something like that, but something that is more very core and heavily tied to the laptop, like your processor, is not something that you change frequently. Similar to that, on the vehicle itself, different parts are designed for different types of assembly and access. Something that is not meant to be removed at all or only has to be replaced in case of a heavy accident versus something that has to be, accessed frequently for service or for charging, right? So different kinds of treatment is given to different parts of the vehicle based on how it is assembled, how it is finally used on the vehicle itself, and different kinds of and this goes all the way to the final instruction manual that is provided to the user, right? We have to keep all of that in mind while designing all of this. And this is sort of a production readiness check that we do by bringing together all of these components. Again, I'm giving a sense of the mechanical side of things, but this also applies to the electronics parts as well, right? Now, one of the parts that I haven't spoken about intentionally till this point, right, is on the software side of things. Now, this is actually core to what we do. A lot of how all of this, is controlled is actually in terms of the bits that are defining the decisions in terms of the motor controller, the vehicle electronics, the battery technology, like the battery pack itself. And all of that is defined by software. So it's basically computationally heavy. It is defining, I would think of it from, bits to electrons. How do the bits control the electrons, and how do the electrons then result in, moving the vehicle or moving an individual on the vehicle, right? So what starts with very early initial requirements on the embedded system software side go into architectural decisions in terms of which microcontroller to use, what are the sort of code guidelines to follow, what are the architectural choices that are done, what kinds of device drivers, how do you build a sort of does it require an operating system, right? Is it a single threaded process? Is it a RTOS that is running? Is it a full-fledged, Linux operating system that is running there? What are the applications that need to be running? What are the base level firmware that is required? What is the device driver? What is the bootloader there? So all of this is sort of being defined at a very early stage. And while the electronics is being prototyped, to some level, get into, more detailed aspects of, testing and optimizing the software, right? So from the point of, I would say things like, you get into detailed aspects of software testing from, hardware in loop tests, you're running optimizations for performance, for memory footprint, for power optimization, right? You're doing end-to-end testing with all of the software. You're also making sure that the code is following certain standards in terms of different programming standards or different MISRA C compliance standards. You're evaluating the code for maintainability, for testability, for clarity. And this is just on the embedded system side, right? There are whole other layers of software that are being built in parallel. We started with a device driver, what is running on a single microcontroller, then goes into, application software, which is running, probably on the TFT of the LCD display, to, the software that is running to transfer information back to our servers in the cloud on Amazon or Google Cloud or wherever it is. And from there, we're talking about how this backend software integrates all of this data and how that finally that data is used either for analytics internally for the company, or how it is displayed to the end user on the app, right? So all of this loop involves software at different levels. And this goes back to my experience, sort of, where I've dealt with some aspects of the software, some layers of this. But my experience is not with entirely from, for example, firmware development. So we have very strong individuals and experts in these areas to sort of define the requirements, to build on all of these design aspects of the software itself. And this is where the entire stack comes together. So when, like, I've had some very funny instances there, from the world that I came in my previous jobs, etc. People consider full stack development, right? They talk about full stack developers and development, where they're talking about, databases and all the way to usable application software. For me today, full stack means completely something else altogether. It's from, the bare bones C programming that you do to run on a microcontroller, all the way to, application software that is running on the cloud. So that is the full stack for me. It is not what I had in mind earlier as well, right? So that is the difference in terms of the software that we come from when you're building SaaS applications or cloud applications to building hardware. We still have to deal with all of that complexity, which means that we have to define the cloud architecture, what goes on Amazon, on Google Cloud, but we also have to define what every single line of code and every single computational cycle that goes on a microcontroller, because there's an inherent power requirement, constraint in terms of the time. For example, if your decision takes a few hundred milliseconds, that affects how the motor will behave on the vehicle, right? So all of this comes together, and this is what we consider sort of full stack development. Yeah, so this is just purely on the software side. I think we're going to be running short of time, so I'll move a little quicker. When we start putting together all of these things, right? So it is both component level tests. It is, what we call pre-qualification, validation. It happens at various stages. From the point of, it has to meet certain electrical pre-qualification tests, like short circuit, under voltage, like over voltage. We do redundancy checks, whether if a software protection doesn't kick in, do you have electronics hardware to deal with that? How do you deal with, environmental conditions? So what we do is we do thermal cycling, accelerated life testing. We do stress testing of different components. We do dynamometer tests. So the vehicle is loaded onto a dynamometer and it's sort of run before it is taken out onto the road. And then we test it on different kinds of tracks, whether it's a city or a highway or a racetrack or a slope or even torture tracks, right? So to stress out the vehicle, which is, very, very undefined surfaces with lots of bumps and, gravel and those kinds of things. So we have a more detailed sort of test plan, but what I wanted to show you was the visuals in terms of what is done in terms of testing, all the way from hardware in loop sort of testing to final testing of the vehicle. And this is what happens at different stages. It happens when a component is ready. It also happens when the final vehicle all comes together and is assembled, right? Then comes also aspects of dealing with final production, right? How do you assemble together all of these things at a very large scale? And this is things that we will encounter, 2 years from now, 3 years from now. There shouldn't be challenges. So how do you plan for that right now, right? And so this is again a pretty big deal, because we are talking about working with different partners. So companies like Electronics Manufacturing Services, which use pick and place machines for the PCB. So these machines are capable of producing hundreds of thousands of boards per day, right? And so how are the components placed on these boards? What is the standard operating procedure for the assembly of any particular PCB, right? Or from the vehicle control unit to, every single board, the battery management system board, to how the battery packs are assembled. What is the guidance that we need to provide to these companies if we are working with different parties, or how are we building the assembly ourselves on certain things that are very core to the intellectual property of the company, right? So how do you, even down to the level of how are these transported, what are the operational requirements of transportation, at what battery level, what charge level should the battery be while being transported? So all of these are, production planning for, start of production and transportation beyond that, right? And then comes, how do you, and the same thing happens in a slightly different way for the mechanical components, right? So I've blurred out certain parts of the screen intentionally because these are images that are not always public. But the idea here is that as these vehicles come together in tens or hundreds, the scale of the problem changes drastically, right? Even if you have a single rejection, that is a lot of time that has been spent and a vehicle will get rejected at the last stage. So we don't want to deal with problems at that stage. You have to be able to identify them way before and sort of make sure that you avoid such a scenario, right? So what you see on the right is, tooled up parts, which means that it is capable of producing hundreds of thousands of units. And that is the scale that we are starting to operate at in terms of planning for production, right? And all of this sort of comes together on the assembly line. Now, there are different types of assemblies, from the vehicle assembly, the electronics, the battery assembly. All of them happen at, co-located or at different places, but this is how it all starts coming together to produce the final product, which is the F77, the first product, the first sort of motorcycle from the Ultraviolet company. And this is the actual product that was running on the Madras Motor Racetrack in pre-COVID times. There's reviews on YouTube out there, but this is how it all came together into being the final product, right? And I'll sort of wrap up the presentation, but this is what we have been working towards for 5 years. It is very exciting for all of us to see all of this come together, because, from the point of seeing a sketch on paper to seeing a product that is actually functional, it's quite a mind-blowing process for us internally as well. And we're happy to share and talk about certain aspects of it. There's a lot of intellectual property that we've sort of built over time, but the entire process is quite phenomenal. And to build a hardware product in India with all of the constraints that we have seen, I think has been a phenomenal journey for all of us. So thank you for your time. Happy to take more questions if we have time. I think Dinesh will let me know if there's more time here as well. So again, very standard question: does the F77 have energy recovery mechanisms like regenerative braking? Yes. Every electric vehicle sort of tends to have that. A lot of EV companies talk about it as though it is a major sort of groundbreaking feature, but it is inherent to the technology, which is that the motor itself can function as a generator of electricity in certain conditions. And that also, of course, leads to slowing down or deceleration of the vehicle. And at the same time, you're recovering energy from the motor and you're turning it into essentially a generator, right? So yes, the vehicle does come with, regenerative braking or, yeah. Okay, so another question is, how do you determine the confidence levels while building high fidelity models, right? So again, this is a combination of, this happens over several stages. This doesn't happen at the initial simulation stage, right? So once you get a sense of the material properties of what is available in India and you sort of run it through an actual test, only then you are able to tell whether your simulation was, close to reality. What was the expected outcome versus what is the realistic outcome. And next time when you do your simulation, you have a better idea, and then you can start to build more statistical models in terms of what is the confidence level that I'm talking about, right? Again, another question: how did your team decide between make or buy for your batteries? Frankly, there were no batteries available for us which could do the job for this performance motorcycle. We're talking about, if you look at the industry, typically electric vehicles have fallen into two kinds of segments: very low powered vehicles in terms of 3 to 5 kilowatts in terms of peak power, scooters, etc. And then there are cars which are, like the Tesla Model S, these kinds of cars which are in tens of kilowatts, and now you have liquid cooling, you have thousands of cells to take that kind of load, and there's nothing in between that we could actually use. So we had to build the batteries ourselves. So this was not much of an option, and frankly, that is where a lot of the intellectual property of the company is today.
Am I audible now? Sorry, some problem with the mic. I had to log out and log in.
Okay, no problem. Yes, I can hear you.
So I'll probably start with the questions that are most upvotes, right? So the first question is, did you guys use lean startup or equivalent methodologies to keep validating your hypothesis and research?
Yes and no. Lean startup makes certain assumptions about, things that you can test with customers also, right? And in this case, when there's a long lead time when it comes to hardware and things like that, you can't really sell a product and then go and refine it like you can do in software, right? Which means that you have to be bang on right about the requirements years in advance of building, selling the product to the end user. So that means that you can't use a typical customer validation approach. You also have to imagine what the requirements will be few years from now. And if the customer has never seen an electric vehicle, has never even imagined an electric vehicle that can beat an IC engine vehicle, how are you going to sort of plan this a few years ahead of time, right? So it requires certain leaps of faith, which are not really viable to, all of your lean approaches. And of course, you can frame it as a hypothesis and see that, okay, is this hypothesis going to pan out few years from now? But the typical time frame to test out a hypothesis is much, much wider and longer in time, right? So I would say it's a little different from that.
Got it. So this is from the earlier your experience, right? You worked in Yahoo, NetApp, and other startups as well. Which among those do you consider as the most critical experience, without which the UV wouldn't UV wouldn't have happened?
I think actually it's that's what I was talking about, right? So it's bits and pieces from all of that. So from Yahoo, I learned how to deal with very large scale systems where you have thousands of requirements coming in, thousands of data points. You have mission criticality of the system coming in. Every second of downtime means the loss. Every minute of downtime means a few $1 million of revenue lost, right? While at the same time, when I talk about the drone company that did not even have a name, I realized the kinds of skill sets that were important, right? This is, I would say, almost 6 or 8 years before we started this company, that I knew that if I have to talk to a person who's designing electronics, this would be the conversation that I would have. And even to build the grammar to be able to talk to someone in a particular industry takes time. So the first time you go and talk to someone from some other industry and you're not from that industry, they'll sort of, you come across as someone who doesn't know anything. And that is always going to happen, right? You will end up making mistakes. So being able to learn how to converse with professionals also is a necessary skill, right? Because that's the only way that you can build something at this scale and size. So again, my experience from that startup also mattered. When it came to NetApp, it was more about working with very early stage research ideas, people who are doing their PhD thesis or, postdoctoral research. How do you sort of bring back market requirements 5 years from now into what is going to be happening in the research lab? How do you build the hypothesis for that? How do you plan for that? So all of these experiences, I would say, has counted. It's not just one that I would say has mattered. It's only when I look back that all those dots now seem to make sense.
Got it. So another very interesting question. What are the scopes of supercapacitor batteries in EV two-wheelers?
Again, so this is an evolving field. We have explored supercapacitors at early stages of design. So there are certain constraints that come with, while supercapacitors have very high power density, they do have very low energy density in terms of the total capacity, usable capacity that works. So while you have limited space on a motorcycle that you see on the screen, if you start filling up supercapacitors in certain areas, you are not making the best utilization. So you are going to benefit on the power where you will be able to get an higher instantaneous or spontaneous power, but at the same time, you're going to be compromising on range of the vehicle.
Okay.
Right? So it's a combination that has to be done. And what we found is that for today's requirements, I think we found batteries that meet our needs. But over time, we do see that supercapacitors will come into it.
Got it. Okay. So it's a suggestion from Raghava. He said it'd be great to have a follow-up talk, deep dive on just the software engineering challenges in designing the system, trade-offs made, and technology choices. It's a suggestion. But again, today we got a completely different understanding of what a full stack developer is.
It's just that it's dispersed, it's across companies, etc. But when it comes to hardware, we don't see that. When it comes to mechanical engineering, electronics design, I think those skill sets are still developing in the market, and which is why my idea was to sort of bring about that and bring that awareness when it comes to building hardware.
Yeah, this is an awesome presentation, because for us it's a rare insight into what is happening out there, right? And very, very inspiring as well.
Thank you, Dinesh.
The next question is about, given the high performance of UV, how did you guys decide with air cooling your key components like battery pack and motor? How was the proper cooling of the modular battery packs ensured?
Okay, this is again a great question. So this was actually a problem, like you were talking about lean startup and all of these approaches, right? So one of the things that we realized was in very early stages is that if the vehicle has to be sustainable, we have to build it in a sustainable way, which means that we use the minimum number of components that to go into the vehicle to achieve the maximum performance, right? And what that means is that if you, for example, add liquid cooling onto the motorcycle, you're adding a radiator, you're adding cooling pumps, you're adding a whole, liquid which requires frequent maintenance, you're adding pathways for the liquid to flow around. Of course, you will achieve, it will become easier to cool the battery pack probably, but it is at the expense of weight. It is at the expense of more number of moving parts on the vehicle. It is at the expense of more, adding another $100 to $250 to the vehicle cost itself, right? So now when we started out, it was an impossible challenge for us, frankly. I tell you, 3 years ago, we said that we will achieve this kind of power output, 25, 30 kilowatts of peak power, and we will do it with air cooling, right? And at that point, it was not clear to us whether we would actually achieve it. But we still decided, this is a shot that we need to take. And it took several years, several smaller experiments on thermal management, on the aerodynamics of the vehicle, the airflow analysis on batteries, on electronics, and real world testing to sort of give us comfort along the way at several intermediate stages that we could actually achieve this. And it was, I think, from the point of where we sort of put that hypothesis forward that we can do this with a fully air-cooled motorcycle and fully air-cooled technology, to the point of it being validated was anywhere from, I think, 2 to 3 years. And so it was a big there was a lot of anxiety within the team also to say that we're going to pull this off because no one has done this before, right? But I'm glad that we have done that today, because that's where the core intellectual property of the company also lies, right? And that's because we've solved something that could not be solved before. And
great.
Just to add to that, that's a combination of electrical, mechanical, fluid dynamics, structural engineering, software, like everything comes into the picture, simulation, to achieve this. And it's not a trivial solution in any sense.
Got it. So fairly easy question. Next one. Do you have any roadmap for economical oriented two-wheeler in future?
I think there are lots of companies trying to solve this challenge. I would not comment on any particular product segment that we will launch after the F77. It's a little too early to talk about that, whether it is other kinds of motorcycles or any other products. But the idea behind building Ultraviolet was to be on building cutting edge technology, right? And that is something that will remain the theme of what we're trying to do. If it's something that is, whether that means economical or, premium, these kinds of decisions will be taken over a period of time. But what we want to be solving is the hard problems, right? And there are problems that will be solved by other companies as well. We don't see us as being the only company in the space, right? But there is the team that we've put together is meant to solve difficult, challenging problems. And we will target those particular problems in a sustainable way as we move forward. That's all I can say right now.
Got it. Does F77 has an in-house developed motor controller? If yes, okay. I don't know whether you can do that. Please share the structure, roadmap for design and development of same.
Can't talk about everything, but I think a lot of work that we do, you've seen the skill set of the team, right? So it's very strong on the electronics, on the software, on mechanical systems. So it's, for us, the way that we determine something, whether we want to build it in-house or not, is based on several criteria. One is there a significant cost advantage to building it out in-house, right? That is one. If not, then really what is the point of building something from scratch again? Second is there intellectual property to be built in this space? Is this a fairly recent new space, which means that a lot of problems remain unsolved? And when it comes to motor controllers, frankly, it is unsolved, right? For example, safety requirements on the software side, on the electronic system, using new materials in terms of the transistors or the MOSFETs. Like, there are so many technologies that have happened that have evolved and come to life in the last 10 years that haven't been applied to motor controllers, right? So there's a lot of intellectual property to be built out even in this space itself. So I would say it's only, I can't comment on it right now, but there's a definite direction there from our end also.
Sure, thank you. The last question is, I currently don't have co-founder for my startup. How do I begin my journey into this and move ahead with prototyping as it requires a team?
Okay, that's I would say it's a difficult problem to solve. So I think what I've noticed is that if you're trying to find a co-founder, it's better to work with someone you have previously worked with in a very uncertain environment, right? So if you just know the other person for a few months, that is insufficient in most cases to start a company with. It would, if the few months happen to be in a situation where both of y'all were, or all of the people involved were in a very stressful situation, you know how the other person behaves. You sort of get a sense of, can I work with this person under very stressful conditions, right? Are they behaving logically, rationally? Are their decisions not being emotional in nature? All of these are more important than pure technical ability, right? And in the long run, those are the things that matter. Of course, technical ability matters. If the person is not competent enough, then you shouldn't even be starting a company with that person. But these are things that, if you don't have the right co-founder, it also makes sense want to be working with, right? So it's not that I will go out of my way to find someone else. It is usually takes time to build that comfort working with people.
That's true. That's true. Yeah, thank you, Niraj. It's as I said, it's a very, very exciting presentation because many of us are from software background, right? Pure software, rather I would say, and going into the like how the hardware or electrical mobility companies are built is a rare insight and like very well presented as well, right? And it's as I said, it's a very, very exciting journey for you, and you guys are literally pioneering how the electrical mobility is going is in India, right? And hope we all remember this presentation or this story as we do remember for Apple and Tesla. Right? All the very best, and thanks a lot for spending your time and all the knowledge that you shared with us on a Saturday. And thanks everyone who participated in this CTO talk, and have a great weekend as well.
Thank you, Shweta. Thanks, Dinesh. Thank you, everyone, for joining.
Thank you. Bye-bye.
Talking to all of you. Thank you. Bye.